So in this second part, we're going to start to look at algebraic expressions. And in the last part, we looked at these sort of single variable expressions, right? We looked at these things that are made of a single variable or a single term, right? Sometimes a single variable, sometimes not. Um, an algebraic expression combines those um, with addition, subtraction, multiplication, and division. We're going to hold off on division for now. That's going to come in a bit. Um, but there's the basic unit of these algebraic expressions, and this basic unit is something that we looked at already. And this basic unit is the monomial. Mono meaning one. And it's something that looks like a for some real number a times x, and x is raised to some power k. And these basic monomials are the building blocks of our expressions. If I combine two of them, I get a binomial. Combine three of them, you get a trinomial. You combine an arbitrary number of them, we'll get a thing called a polynomial. Now, this thing called a polynomial, we will see this term a lot, especially as we get to the middle of the quarter. We're going to be doing a lot of work with polynomials, but I'm going to introduce them to you now and just trust that they will come back again in a big and hopefully fun way later. But a polynomial, um, polynomials are always, as we say, in a particular variable, right? There's this unknown component of these monomials, um, and that variable, we say that it is a polynomial in a variable x, right? So you might have a polynomial in x, a polynomial in y, is an expression of the form, and it looks like this. I'm going to use a different color. It looks like an x to the n plus a n minus 1 x to the n minus 1 plus, and so on and so forth down the line to say a 2x squared plus a1x plus a 0. And here's what we'll say. We need some qualifiers to explain more what we're talking about, where my a0, a1, and so on up to an, all of these are real numbers. N is a non-negative integer. Um, so n is some non-negative integer, right? So it's a non-negative whole number, right? It could absolutely be 0. Um, and further, if a sub n is not 0, then we say the degree of the polynomial is n, right? So, if you have, say, x cubed plus 5x squared, that is a degree 3, right? Because n, our leading term, our biggest term, right, with the highest power, um, is an x cubed, right? So it's a degree 3 polynomial. Further, one um, other piece of note, the monomial, ak x to the k, right? these monomials, right, which make up the polynomial, right? We're adding a bunch of these together. Each of these monomials are called the terms of the polynomial, right? So a polynomial with one term is a monomial, a polynomial with two terms is a binomial, and etc. and etc. Now these algebraic expressions, we're going to be doing algebra with them, right? We're going to be combining them in various ways. The first way that we can sort of talk about is the addition and subtraction. And they add and subtract in exactly the way you would expect, right? You would use the distributive property on any minus signs, and you collect like terms, right? So for example, let's say we have x cubed minus 6x squared plus 2x plus 4. This is a degree 3 polynomial because our highest power is 3. And we're going to add to that, say the polynomial, don't know how that happened. It's weird how that keeps happening. Let's say we add to that x cubed plus 5x squared minus 7x. Well, as I said, this is essentially just combining like terms, right? So let's first look at our x cubed terms. It looks like we have 1 plus 1. So we have two of those. We have two x cubes. X squared, it looks like we have minus 6 and plus 5. So it looks like we have a total of minus 1 x squareds. X's, it looks like we have 2 and minus 7. So I would say that that comes out to minus 5 x's. And we have 1 plus 4 here. And as I said, they add in the exact way you would expect. Let's copy this down. I have the nice addition of being able to do that with the iPad. But let's change this a little bit, and instead let's subtract these two polynomials. But as I said, all we need to do is distribute this minus sign into each of these terms, and we get an easier expression to work with. X cubed minus 6x squared plus 2x plus 4 minus x cubed minus 5 x squared, and a minus a negative 7x is a plus 7x. Collecting like terms again, we see 1x cubed minus 1x cubed, so we get 0x cubed. We have minus 6x squared minus 5x squared for a minus 11x squared. Looks like we have 2x plus 7x for a plus 9x. And we still have this trailing plus 4. And simple as that, we can add and subtract these polynomials. We can, however, move on to something a little bit more interesting and engaging, right? Let's talk about instead multiplying polynomials. So your first exposure to multiplying polynomials together was probably a little bit something called the FOIL method, right? We might have A plus B times C plus D, right? Again, since we're doing this in college now, we're moving towards a general approach to these ideas. So we have two general binomials here, A plus B times C plus D, and you would use FOIL to solve this, right? You would go first, so AC, then you would go outer, so it would be plus AD. You would go the inner two, so plus BC, and the last plus BD. Now we can do some examples of this, right? Let's say, 2x plus 1 times 3x minus 5. When we do our first term, it looks like we get 6x squared. Our outer term gives us minus 10x. Our inner term gives us plus 3x. And our last term gives us minus 5. When we simplify this, that should leave us with 6x squared minus 7x minus 5. And there's nothing special about having to use, two linear terms like this. We could do something like x squared plus 2 times x to the 5th plus x. And this breaks up in a similar way. We would do our first terms, which gives us x to the 7. Our second term gives us x cubed. Our third term gives us 2x to the 5th. And our last term gives us 2x. Expanded, nice and simple. But what happens when you're given more complicated situations, right? What happens when you want to multiply, say, a binomial times a trinomial? And the way to do that is we actually want to look a little bit more into how we get this, right? Why does FOIL work? And let me show you, right? FOIL is just a particular case of the distributive property, right? A plus B times C plus D. What this is, right? This is equal to A times C plus D plus B times C plus D, right? This is just what it means to distribute one of these into the other. But now we can use the distributive property once again into this. And we get AC plus AD plus BC plus BD. And if you look, this is our first term, this is our second term of the FOIL, our third term, and the fourth term. So this really strange thing of FOIL that we have internalized and many of us have been using for years and years, well, it's just the distributive property. So that means that when I give you something like this, right, say 2x plus 3 times x squared minus 5x plus 4, when I give you something like this, well, we can just go back and use that distributive property to expand it, right? This is equal to 2x times x squared minus 5x plus 4 plus 3 times x squared minus 5x plus 4. Well, now we're just doing a simple distribution, right? We can take these one at a time and then combine like terms. 2x times 2x times x squared is 2x cubed. 2x times minus 5x is minus 10x squared. 2x times 4 is plus 8x. And we get 3x squared. 3 times minus 5x is minus 15x. 3 times 4 is 12. And when we collect like terms, looks like we have 2x cubes, we have minus 10x squareds, and 3x squared, so that tells me we have the total of minus 7x squareds. We have 8x and minus 15x. We combine that, we get another minus 7x. And then we have this trailing 12. And this is how we can do those expansions. It's just the distributive property. Just as with our exponents and our radicals, there are some sort of special product formulas to know, right? Some things that become handy for us to recognize quickly because they just come up so often. And I am actually going to switch to a new page so that we can have sort of enough room to write these. These are what we call the special product formulas. So the special product formulas, as I said, are just a set of commonly used expressions um, and their expansions. This is useful for um, quickly doing algebra as well as factoring. So let's say we have A and B are real numbers, right? As well, they could be algebraic expressions, right? There's nothing special because like all of these algebraic expressions are built with real numbers as well, so they would stand in here as well. Here are the special product formulas. One, we have A plus B times A minus B. This is the sum and difference of the same term. This is A squared minus B squared, right? You'll often see this called the difference of squares, right? Because it's this square minus this square. Two, we have, say, A plus B squared, and we want to expand that quickly. That's A squared plus 2AB plus B squared. Similarly, if we have A minus B all squared, that's A squared minus 2AB plus B squared. In fact, with some simple algebra, this one here will directly give you this one, right? You just let B here, you let B here equal minus B, and you carry on some arithmetic. Going forward, we have our next one. Let's say we have A plus B cubed. Well, that starts similarly. This is A cubed plus 3A squared B plus 3A B squared plus B cubed. What if we have A minus B cubed? Well, noticing how this one went plus minus plus, we should sort of expect, right, this to go plus minus plus minus. And in fact, it does. A minus B quantity cubed is A cubed minus 3A squared B plus 3AB squared minus B cubed. Once again, you can use this with a quick substitution to directly give you that answer. So what I want you to recognize, right, is going this way, we're expanding, and going this way, we're factoring, right? There's two more that sort of go along with this difference of squares, and that's the sum and difference of cubes, right? So number 6, say you have A cubed minus B cubed, right? You want to, in this case, actually factor this, right? You want to take an expression and turn it into something multiplied by something else, right? Well, A minus B cubed, that's equal to A minus B times A squared plus AB plus B squared. And number 7, the last one on this long list, is a cubed. Is b cubed. That's a plus b times a squared minus ab plus b squared. Now, unfortunately, I can't go through, some sort of beautiful proof of each of these to give you an intuition for how or why they work. I really wish I could. We just unfortunately don't have time in this course to do this or to do that. You definitely want to memorize these 7. You won't ever be like directly tested on them, right? You won't get a quiz that's like, expand this. But they will come up throughout the quarter, and it will pay you back well in time if you can just recognize these as each other. But let's not just write down arbitrary expressions. Let's do some examples, right? So let's say we're being asked to expand this x squared plus y cubed all squared. Well, this is the same thing that we saw here, right? So this is, we can call a squared or x squared a and y cubed b. So this is x squared plus 2 times x squared y cubed plus y cubed squared. And using the exponent laws that we just looked at, this is x to the 4th plus 2x squared y cubed plus y to the 6th, right? Because when we have this exponent to a power, we multiply. Our next one, let's say take a look at x squared minus 2, and let's cube that, right? Well, we can call our x squared a and our minus 2b. Since we're cubing it, that's going to be x squared cubed. And we have a minus here, so we know it's going to be minus 3 x squared squared times our b, which is 2, plus 3 times x squared times our b squared. And it's going to be minus rb cubed. We simplify this. 2 squared cubed is x to the 6th minus, 3 times 2 is going to be 6. Looks like x to the 4th. Plus 2 squared is 4 times 3 is 12. X squared, and we have a minus 8. One more for you on these. What's x plus y minus 1 times x plus y plus 1? Now, as we saw before, you could absolutely just use the distributive method here. It would be, in fact, rather quick, but there is a slightly faster way to do this. And let's observe that we have x plus y in both of them, and we have 1 in both of them, and it's plus here, and it's minus here. This is a difference of squares, right? This is whatever we called a squared minus whatever we called b squared. So now we turned a trinomial times a trinomial into the square of a binomial. But we know this, right? This is x squared plus 2xy plus y squared. And then we need this minus 1. So instead of doing 9 operations, right, that's how many it would take to split all this up and do all of the multiplication, we did this in 2 simple steps. And for our final little section of this lecture, we're going to look at rational expressions. And the definition of a rational expression is quite simple. It is just simply the quotient of two polynomials. Right, so we're dividing one polynomial by another, right? You might have 2x over x minus 1, or the polynomial 3x, or x cubed minus x over x squared plus 5x plus 6, or, say y minus 2 over y squared plus 4, or even say the polynomial like x cubed plus 3, right? 1 is a polynomial, so this is still a polynomial divided by a polynomial, albeit not a very interesting one, right? And the first thing that we need to talk about the moment we start dividing by things like this is a concept called the domain. And the domain is something that we will come back to time and time again over this quarter. Bad things happen when we divide by 0, right? It doesn't matter what math class you're in, you're not allowed to divide by 0. Similarly, whenever we attempt to perform operations that aren't possible, things go bad. Often we just get something that's undefined. So it becomes helpful for us to be like, well, we want to avoid where it's undefined. So where is it defined? And that's what the domain is, right? The domain is everywhere our expression is defined. And this is a really important concept that, again, as I said, it will come up time and time again throughout the course, right? So let's just look at a few some simple examples first, right? So we have an expression, and we have its domain. First one, sort of the categorical example of dividing by 0, we have 1 over x, right? You can do this everywhere except for where x equals 0. So my domain is a set, the set of all x, where x does not equal 0. Another way to write this, if you want to use that set minus, is the real numbers minus the set containing 0. Another common one is our square root function. Remember, our square root is not defined for negative inputs, so our domain is everywhere where we're greater than or equal to 0. What about something like this? Say the square root of x over x minus 5. Well, there's two things that could potentially go wrong here, right? There's two places where we're doing something that's not allowed. Well, the first one is that we don't want to divide by 0 here. So part of our domain needs to be where x does not equal 0, or where x minus 5 does not equal 0. Our second part is we can't put negative inputs in, right? So our domain sort of comes in two parts. We're the set of all x, where, first, to deal with our radical, we have x is greater than or equal to 0. And all of those inputs are fine on the bottom, except for if x equals 5. If x equals 5, we have 5 minus 5, we get 0. It's all bad. So we can say a comma, meaning sort of and, x does not equal 5. Now that we've discussed domain, we can talk about combining these, right? We're going to actually do it the opposite way that we did polynomials. We're going to talk about multiplication first. And for multiplication, once again, it proceeds as we would expect, right? So let's do one quick example here. We might have x squared plus 2x minus 3 over x squared plus 8x plus 16 times 3x plus 12 over x minus 1. And this proceeds the way that you would expect, right? We multiply, this times this and divide it by this times that. Before I do that, however, I'm actually going to factor as much as I can. This numerator here is going to factor to, it looks like x plus 3 and x minus 1. I can factor out a 3 here, so we get 3 times x plus 4. On the bottom here, this is a perfect square, right? This is x plus 4 squared, and x minus 1 stands on its own. What I want you to notice here is we can cancel these x minus 1s, and we can cancel one of these x plus 4s with that, and we end up with the final expression 3 times x plus 3 over x plus 4. Nice and simple. For division, I'm going to sort of write this over in the corner. So for, I'm actually not in green, I'll say do this purple. For division, we're going to follow the way that we divided fractions made of real numbers, right? A over b divided by c over d is a over b times d over c. And it will be rare that we use this explicit division symbol, but here in the beginning it is kind of handy. So we can do a quick example of that. Let's say we have x minus 4 over x squared plus 4 times, divided by x squared minus 3x minus 4 over x squared plus 5x plus 6. Well, first thing we need to do is flip this, right? We get x minus 4. I can factor, so that should be a minus. I can factor this bottom part to x plus 2 and x minus 2 because it's the difference of squares. And I'm going to multiply that by this guy. We get x squared plus 5x plus 6 over x squared minus 3x minus 4. Continuing to factor, we have, looks to me like x plus 2 times x plus 3 on the top, and x minus 4 and x plus 1 on the bottom. Canceling common factors, I see an x minus 4 and an x minus 4, an x plus 2 and an x plus 2, and so I can write this as x plus 3 over x minus 2 times x plus 1. For our concept of multiplication, as I've said time and time again, we sort of proceed as expected when we're adding or subtracting these rational expressions, with the additional step of we need a common denominator, right? So let's say we have 3 over x plus 1 plus x over x plus 2. In order for us to add these two expressions, we do need a common denominator, so we need to multiply by a fancy 1. 3 over x plus 1, we'll say we'll multiply this by x plus 2 over x plus 2, and we have x over x plus 2 times x plus 1 over x plus 1. Now we perform this sort of internal multiplication before we add them. And we get, looks like 3x plus 6. I'll keep these two separate. X plus 1, x plus 2. Plus, looks like x squared plus x over x plus 1, x plus 2. And now that we have a common denominator, we can simply add the numerators, leaving the denominators the same. When we do so, looks like we're going to get x squared. 3x plus x is 4x plus 6 over x plus 1 times x plus 2. Finally, what we can do with these concepts of addition and multiplication and division of these terms, we can look at something called compound fractions. And compound rational expressions are essentially when you build rational expressions with rational expressions, right? So we'll do one last example of that to sort of finish up this lecture. Let's look at the compound fraction x over y plus 1 over 1 minus y over x, right? This is a rational expression divided by a rational expression. The first thing that I want to do is sort of deal with each of these terms individually. I want to get a common denominator here and a common denominator here. So my common denominator of the first one, well, I want this to be over y. So we'll have x over y, and we're adding just one, so that will be y over y. And we're dividing that whole thing by x over x minus y over x, right? Where I did the same thing here of multiplying 1 by x over x. Now I can add with my common denominator, and I can get x plus y over y divided by, that should be a minus, x minus y over x. But what this is this is the division of two rational functions. So I can take the reciprocal of this one and multiply. So this is x plus y over y times x over x minus y. And now I simply perform this multiplication, and I'm going to leave it like this: x times x plus y over y times x minus y. And we've transformed this, honestly, rather ugly looking compound fraction into this much nicer rational expression. That completes our first lecture. If you are available this Wednesday at 4:10, stop by the office hours, and we can sort of introduce ourselves and meet each other